In this video, we're going to talk about Young's double slit experiment, or simply double slit experiments in general. Now, normally the setup of these experiments are a very rough drawing. You have some sort of opaque material with two very thin slits in it. A light is shined sort of on this double slits by a laser or whatever it may be. In the case of Young's double slit, it was sunlight, and this light is shined through here, and this is called incident light. This causes two waves, ripple outwards from these two slits. These waves interfere with each other and are detected on a back wall, and that causes an interference pattern, and where the interference pattern looks like this. We have these light regions and dark regions and light regions and dark regions and light ones and dark again, looking like this. Now these light points are points where we have constructive interference, where these two waves from these two slits interfere constructively and cause light parts, but the dark parts are where these two waves interfere destructively and cause these dark parts, or no light to shine, or very little light. So we're going to do analysis of this experiment, and we're going to see where we can work out where those light and dark slits are and understand how the light interferes with itself. We'll take a bird's eye view of the situation. Let's see if we had, this was our, do it like this. So these two gaps here are two slits, and we have a wavefront coming in. Now this wavefront is just the light coming from the whatever you're using, the sunlight or the laser in modern day cases, and it's simply travelling to the right towards these double slits. So each of these spacing is going to be one wavelength, and they're travelling to the right. And they're going to get to these double slits, and they're going to be diffracted. Now, depending on the width of these slits, it's going to be diffracted at a certain angle. We saw in a previous video that the equation we used for the angle of diffraction is theta is equal to the inverse sine of the wavelength divided by the aperture, or the A value. The A value is just going to be these little width here, the width of the slits here. The wavelength value is going to be these wavelengths. So depending on the proportion of the wavelength to the aperture would be, at what angle these things are going to be diffracted. So you can imagine, we're going to get a spreading out of waves, something like this. I'll draw these in first, and you'll see in a minute. The waves from this point are going to go something like this, where they're going to spread out or diffract. The waves from the other slit are going to do the same thing. They're going to spread out along their plane at their angle, which is going to be the same angle as this first slit there. And what we have here is we have two waves now. Even though we have one source, the source is over here, which is the laser or the sunlight, which is emitting this light at this particular wavelength. Because we have two slits, we're going to have two sort of light waves coming in, and they're going to interfere with themselves. So the same source, but we end up with two light waves. And they travel outwards, they interfere with themselves. We have the detector here, and the points of constructive and destructive interference. You could draw them here. There's our maximum sort of constructive interference right in the middle of those waves, and we have a dark spot, then a light spot, then a dark spot, then a light spot. So basically just drawing the experiment again from a bird's eye view, just to see what's really going on here. Now, how can we do an analysis for this situation? Well, first off, what is our equation for the interference of two waves? What I mean by that is, if we wanted to know, if we knew, we had the two equations for two different waves is in two dimensions, what is the equations for our interference of these two waves? Now, we use this equation here where we say the change in phase, or the phase difference, is equal to 2 pi times delta x over the wavelength plus our inherent phase difference. If you haven't seen this equation before, I suggest you watch some videos in the wave mechanics playlist. It will show you how this equation is derived and understand how it really works, but I'll go over it quickly here. We are looking at the phase difference between these two waves. The phase difference depends on the path length difference, which is simply the length of which the wave has travelled to a point. Like if we were picking this point here on the wall, this wave from here has travelled this distance, while this wave here has travelled this distance, and the path length difference is simply this distance, minus this distance, so the difference in the distance travelled. So that would be the path length difference, where this might be, x1 distance, this is x2, and our delta x is equal to our x2 minus x1, which equals whatever value that might be. Our inherent phase difference is these waves are going to have their own phase as they start. So if you have two sources of a wave, they normally have a different phase, or they can have a different phase. Now in this case, we can forget this value because this is coming from one single source. So it's only going to have both these waves can have the same phase because they're coming from the same source. So we can forget this value here, and we can simply say the phase difference between these two waves is equal to 2 pi times the path length difference divided by the wavelength. So I hope you understand where this came from. If you don't, again, watch the videos in the wave mechanics titled Interference or points of constructive and destructive interference. So this is the equation here for the phase difference of a wave. If we wanted to look at this point here, or this point here, or this point here, we would just look at the phase difference at that point and see if we get constructive and destructive interference. Well, what are the points of constructive and destructive interference? Well, we said also in a previous video that we have constructive interference when the phase difference is multiples of 2 pi, or we say m times 2 pi, for m is an integer. Oops. What that means is, if the phase difference is, we could say m equals 0, m equals 1, m equals 2, or any number like that. If m equals 0, our phase difference would be 0, because 0 times 2 pi, and that would cause constructive interference. Or it could be, constructive. Or it could be 1 times 2 pi, or 2 times 2 pi, which is 4 pi, or anything like that. Our points of destructive interference are points where the phase difference is equal to, I think it's m plus 1/2 times 2 pi. For the same thing, m equals 0 or 1 or 2 or any number like that, and that's the points of destructive. So the points of destructive are going to be where we get no light because both waves have the destructive interference, they cancel each other out. The points of constructive interference, where the points don't cancel each other out, they in fact add to each other, and we get these light points here. This point here is what we call the central maximum, because simply this is going to be the lightest point out of all of these, and what we call here, these are called interference fringes, or you could think of them as secondary maximums. So I've sort of outlined the experiment in this video, and I've sort of talked about constructive and destructive interference, but now in the next video we're going to actually look at these path length differences and work out what are the points where these constructive and destructive interferences happen. So I hope to see you in the next video.